So in today's video, we'll talk about half-range Fourier sine series or cosine series. Now, what is Fourier series? When we can write down a Fourier series for a given function. So let's try to understand that. So if a given function fx is well defined in a certain interval called minus L to L, and it's periodic beyond this interval with the period 2L, and fx and f prime x both are piecewise, at least piecewise continuous in the interval minus L to L, if these conditions are satisfied, then we can write down a Fourier series expansion of function fx if x is a point of continuity in the interval minus L to L as this, where an and bn are called Fourier coefficients, where n is equal to 0, 1, 2, 3 for an and 1, 2, 3 is for bn. These conditions are called Dirichlet conditions. But we have to keep in our mind that these Dirichlet conditions are the sufficient conditions for writing down a Fourier series expansion of a given function fx. They are not the necessary condition. That is, if these conditions are satisfied, then certainly we can write down a Fourier series expansion of a given function of this kind. But if these conditions are not satisfied, even then there are chances that we can still write down this kind of expansion. We may or may not be able to write down. So these are sufficient conditions but not the necessary one. That we have to keep in mind. What is piecewise continuous? Let me explain that. Piecewise continuous means if there is any discontinuity in this interval, so that should be of finite type, and those discontinuities should be finite in number. What does it mean? Let me explain in a more simple way. If this is the given interval minus L to L, suppose if we can divide this given interval in several subintervals in such a fashion that these two functions fx and f prime x are continuous functions within these subintervals, and if there is any discontinuity in fx and f prime x, that lies at the boundaries of these subintervals, and that discontinuity should be of finite type. That is, the value of the function fx and f prime x should not become infinite at the boundaries of those subintervals. So if these conditions are satisfied, then these functions fx and f prime x will be called as piecewise continuous function in the given interval minus L to L. If x happens to be the point of continuity in this interval for fx, then this series in the right hand side converges to fx. If it is a point of discontinuity, so because we have just discussed in the piecewise continuous function, we may find points where the function fx and f prime x is not continuous. So if this f is a point of discontinuity in minus L to L, then the left hand side will have to be replaced by if x is a point of discontinuity the LHS of 1 will be fx minus 0 plus fx plus 0 by 2, the average of these two. Okay, this is called Fourier series expansion of a function fx. Now, there is what is half-range Fourier series sine or cosine series. So sometimes we have given a problem. Suppose we have been asked to find out a Fourier series expansion of a given function in the interval 0 to L, for example, instead of minus L to L. So usually whenever we are asked to find out a half-range Fourier sine series or cosine series for a given function, we are generally given the function to be defined in the half range 0 to L, thus giving the name as half range Fourier sine or cosine series. So if we look carefully, if the given function fx is an odd function of x, for example, if it is an odd function of x, then fx is an odd function and cos is an even function of x. So the product of these two will become odd function. Now by the property of the definite integral, if this integrand is an odd function of x, so this an will vanish. All an's will vanish. So in other words, we will have all an's 0 in this series written in the right hand side of equation 1. And what will happen to the coefficient bn? Fx is odd, this is odd, the product of these two odd function will be an even function, integrand will be even, and then we have it by using the property of definite integral, we will have twice of over L, 0 to L, and this. Okay, so in other words, we will not have this cosine term in the expansion of that odd function fx in the right hand side. We will have only sine function. So this will have only the sine terms in the expansion of x, it means it is called Fourier Sine series. And why half range? Because in the integral will go from 0 to L. Similarly, if fx happens to be an even function, fx is an even function, cos is an even function, so product of two even function is again even function, and then its integrand is even. So by the property of the definite integral, we can write down 2 by L, 0 to L, and we'll have non-zero ans. But in case of Bn, we will if fx is even, this is odd, product of these two will be odd, and the integrand will be odd, and this by the property of this definite integral, this Bn will be, all these Bn will be vanished. In that case, we will have only the cosine terms in the expansion of that even function fx in the right hand side. So that will contain only the cosine function in the expansion of the function fx, and this is known as half range Fourier cosine series, because this integral will be 0 to L using the property of the definite integral. Okay, so let me quickly write down what I just said. From here, if fx is odd function of x, that is f of minus x is same as minus of fx. So from let me give a number 2 and this is number 3. So from 2 we see that I have just explained that if it is fx is an odd function, the product of these two will be odd functions. So we will have an will be 0 and bn will be equal to, this is an odd function now, or this is also an odd function, sine is an odd function of x. So the product of two odd function is an even function. So this is even function. So if I use the property of the definite integral, this I can write down as 0 to L fx sine n by x by L dx. So in other words, in the expansion of fx, only those terms will survive which have Bn. All n will be 0. So it is essentially would be the Fourier sine series of the odd function fx. Similarly, for if fx is even, the situation will be reversed. That is, f of minus x is same as fx. So from 2 and 3 we can see that ans are non-zero this time, even function, product of two even function is even, so an will be 2 over L, 0 to L fx cos n pi x by L dx, and bn's will be 0 because this will be an even function, this will be an odd function, product of these two will be an odd function, and this will become 0. Okay, so these are known as Fourier half range Fourier sine or cosine series, because you see the half ranges there. Now let's try to solve one or two numerical examples to make this even more clear. How do we apply this in the numerical problems, for example? Okay, so let's solve a numerical problem based on what we have just learned. So this is the given question that we have been asked to expand the fx equal to x function in the x defined in the range minus pi to pi, and this function is periodic beyond this interval p equal to 2 pi, and we have been asked to find out its Fourier series. So let's see how to do that. So now what we observe that this function is actually an odd function of x, because if I replace x by minus x, this will give me minus x, which is minus of fx. So this is an odd function. So what we are supposed to get in case of odd function, we are supposed to get all ans to be 0. So let's try to see that. So what is the value of an? An was, the formula for an was 1 by L minus L to L fx cos n pi x by L dx. Now you see, if I compare with the standard interval that I had written down, minus L to L. So if I compare, L is equal to pi here, and the period 2 pi is equal to 2L, because in our standard case we had taken period to be 2L. So L is equal to pi here. So if I write down this an 1 over pi minus pi to pi, fx is x cos n pi x by pi dx. Okay, so pi cancels out, so it's become cos nx. So this again, now we see the same logic. X is an odd function, this is an even function of x, so this are supposed to be 0. There will come out to be 0. In case of Bn, however, what we see that is 1 over L. 1 over L is 1 over pi now, so minus pi to pi again x sine nx dx, sine n pi x by L. L is pi, so I've simply written it down as sine nx. So if I again see this is an odd function, this is an odd function, product of these two will be an even function, so I can write down that 2 over pi 0 to pi x sine nx dx, which is equal to 2 over pi. I have to solve this definite integral, minus cos nx over n 0 to pi minus cos nx over n dx 0 to pi. So if I solve it, so what do I get? I get the following. If I put pi here, so this will become 2 over pi into minus pi cos n pi over n plus 0. Okay, and then this will go here, minus minus plus 2 over pi 1 over n, and cos nx integration will be sine nx by n and 0 to pi. Okay, so if I put, for example, upper limit in this will come sine n pi, which is 0, because if whether n is odd or even, sine n pi is always 0. Similarly, if I put the lower limit, sine 0 is also 0. So this part is going to give me 0 contribution. So this is actually 0. So what we are left with, this portion only. So Bn will be equal to this, which pi cancels out, and this will become minus 2 over n. So this will be essentially equal to, if I write down, pi cancels out, minus 2 by n, and cos n pi is minus 1 to the power n, because if n is even, cos n pi is equal to plus 1. If n is odd, cos n pi is equal to minus 1. Cos pi is minus 1, cos 2 pi is 1, and similarly. So what we observe that all n's are 0 and bn's are this. It means what is the Fourier series of fx? Finally, the Fourier series of fx is equal to, so Fourier series of fx equal to what again? So this is fx is equal to summation and tending from 1 to infinity, or an's are 0, so no cos term, only sine term. So bn sine nx, which is equal to summation n tending from 1 to infinity. Bn is minus 2 over n minus 1 to the power n sine nx, which is equal to, for n equal to 1 case, it is 2 sine x. For n equal to 2 case, it is minus sine 2x. For n equal to 3 case, it is plus 2 over 3 sine 3x, and so on and so forth. So we find that since fx was an odd function, fx equal to x, so we find only the sine terms in the expansion of for given function fx equal to x. Now let's have a look at different kind of an example, where suppose if I modify the given problem little bit in this fashion, that we have been asked to find out the Fourier cosine series expansion instead of Fourier sine series expansion of the same function fx equal to x, which is defined in the half range now, 0 to pi instead of minus pi to pi. And with, so how do we solve such type of problems? To solve such type of problems, the first step is to plot the given function. So what is the plot of the given function? This is my fx, this is my x, for example, and from 0 to pi, if I plot the function from 0 to pi, so what will be, this is a straight line. Okay, now it's an odd function, and it is defined in the half range, and still we have been asked to find out this Fourier cosine series. But we know that for an odd series, to find out Fourier sine series is a natural thing. But we have asked to find out Fourier cosine series, then we'll have to really redefine our function in such a fashion that if we extend its interval from minus pi to pi, that it becomes a becomes an even function, so that we can write down its Fourier cosine series. So how do we do that? Let's have a look on that. So if I extend my interval from minus pi to pi instead of 0 to pi, and I want to make it an even function, then how this graph should look like for an even function? The property is that f of minus x should be equal to f of x. It means if I replace x by minus x, I should get the same value. The function should return with the same value. So for that, I will have to plot the function like this, because whatever the value of function fx here for x, similarly for negative, it has the same value. Okay, now we have to make it periodic also, so that we can write down its Fourier series, and the period will be so it's now our extended interval is minus pi to pi. Okay, and the period, I have to make it period with period 2 pi. So let's say, suppose I write it 2 pi, so, and this is minus 2 pi. So what is our first step? First step was to extend the definition of a function in the extended interval in such a fashion that it becomes an even function, because we have been asked to find out Fourier cosine series. Had it been an even function already, and we have been asked to find out this Fourier sine series instead of cosine series, so then we would have done the same exercise in such a fashion, then in the extended this region minus L to L in general, this function fx becomes an odd function, so that we can write down this Fourier sine series. Okay, so let's do that. So now we have to make it periodic also, so that we can write down this Fourier series. So it is periodic with let's say with period 2 pi, so this should return with the same value as 2 pi, as it has 0, and so it will be something of this kind. And for whatever it has 0, it has at minus 2 pi also, so it will be something of this kind. So this will be the plot of this function. Okay, whatever it has value here, exactly minus 2 pi, it will have value here. Okay, same thing for this is also true. Whatever it has value as pi, so it will have same as value as minus pi. Okay, so this is how it goes. Now how to write down this Fourier cosine series for such a function? Now it's an even function. Okay, so we can actually straight away use the formula how to write down for Fourier cosine series. All bn's would be 0 for Fourier cosine series, and all an's will be given by the formula 1 over L, which is pi here. If we compare, minus pi to pi fx cos n pi x by L. L is pi, so I have to write nx dx. Okay, now since we have made it deliberately even function, this is an even function, so product of two even function is an even function, so I can again write down directly this as this, cos nx dx. So we have to solve this. So this will become, so for a0 we'll solve separately, because if I put n equal to 0 here, so this will become 1, and this will give me 2 by pi 0 to pi and fx dx. Okay, so this will become 2 over pi fx is x, 0 to pi, fx is x dx, so this means 2 over pi pi square by 2, which means, okay, so we get a0 as pi. Now what about others, an's? So let's calculate for other an's. For other an's, for example, the an's would be equal to 1 over pi, and in this case n is equal to from 1, 2, 3 and so on, because for n equal to 0 we have solved it separately. So an equal to 1 over pi, sorry, let's rather 2 over pi using this formula, 0 to pi x cos nx dx. So this will give me 0 to pi, first we have to solve this definite integral, first function as it is, integration of second, and 0 to pi minus differential of first, and the integration of second, and this integration 0 to pi. So if I solve it, so if I put, for example, the upper limit in the first part of this bracket, so this will become pi sine n pi. Sine n pi is 0, minus if I put the lower limit 0 here. So this first part is actually 0. So what we get is minus 2 over n pi, and the integration of sine nx is minus cos nx over n, and we have to apply the limit 0 to pi. So minus minus become plus, 2 over n square pi, 2 over minus become plus 2 over n square pi, and cos n pi minus cos 0. So this become cos n pi minus cos 0 is 1. Okay, so this is the result that we get. So if we write down the Fourier cosine series of this given function f(x) equal to x, that becomes fx is equal to x is equal to, this is Fourier cosine series in x belongs to 0 to pi. So this is a0 by 2, that is pi by 2, a0 is pi here, plus summation n tending from 1 to infinity an cos nx, and all bn's would be 0, because this was an even function, so that we made it derivative of the even function. So pi by 2 plus summation n tending from 1 to infinity. So this become an value is this 2 over n square pi cos n pi, which is minus 1 to the power n if we wish, and minus 1 cos nx. So this is a Fourier cosine series expansion of the given function fx in the interval 0 to pi. This is how we solve this problem. Okay. So in short, let me recapitulate what we have learned in this video. We have learned in this video, first of all, what are the Dirichlet conditions to write down a Fourier series expansion of a given function. Then what is a half range Fourier series, if it is defined in the interval, half interval 0 to pi, if a given function is defined in this interval, and we have been asked to find out its Fourier series expansion, and if depending on the function is odd or even, we get the sine or cosine terms in the expansion of the given function, that becomes a half range Fourier sine or cosine series. Then the third case, if given function fx is an odd function by nature, fx equal to x, and it is defined in the half range, and we are still asked to find out its Fourier cosine series, for example, in this case, as we have done. So how to do that? The first step is to plot the function, and then to make it, depending upon the requirement, if we have been asked to Fourier cosine series, we have to make it an even function in the extended interval minus pi to pi or minus L to L in general, and then write down is Fourier series expansion according to the half range Fourier series formulas.